Question 11. Right, I need to show that x minus 2 is a factor of this function of x. So I'm going to evaluate the function when x equals 2 and see if it equals 0. And lo and behold, it does. So f of 2 equals 0 implies that x minus 2 is a factor. Okay, hence or otherwise, find the exact solutions for the equation f of x equals 0. So I'm going to have f of x, which is x cubed plus x squared minus 5x minus 2 equals 0. I'm going to factorise the left-hand side. So it's going to be x minus 2. And then I'll factorise that, and that will equal 0. Let's factorise it by inspection. I'm going to have an x squared there. That's going to give me minus 2x squared. So I'm going to need plus 3x. That's going to give me minus 6x. And so I'm going to need plus 1 there, which also works with my minus 2. Right, can I factorise that any further? Do you know, I don't think I can. So I'm going to have my solutions when x minus 2 equals 0, which would imply that x equals 2, or of course, when x squared plus 3x plus 1 equals 0. Now I can't solve that by factorising it, so I'm going to use the formula. I think x equals minus b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. So that's going to be minus 3 plus or minus the square root of 9 minus 4, which is 5 over 2. So my solutions for this equation are that either x equals 2 or x equals minus 3 plus root 5 over 2 or minus 3 minus root 5 over 2. And that is question 11 complete. Question 12. Right, I know that x minus 1 is a root of this, so that means that x plus 1 is a factor. So I'm going to continue to factorise it by dividing that cubic by x plus 1 by inspection. So that's going to give me 2x squared, gives me 1x, gives me 2x squared, so I'm going to need to minus 7 of them to get minus 5, gives me minus 7, so I'm going to need to add on 3. Quick check, minus 1 times 3 is 3. Good. Okay, so my roots of the equation are going to come from when this equals 0 and from when this equals 0. Let's have a look and see how I can find values of x that will make that equal to 0. And let's try factorising it. That would be 2x here and an x here. I'm going to need this minus and a minus, give me the plus 3, 1 and 3. There you are, 3 there, and 1 there gives me the minus 7x. Good, so the other roots of the equation are going to be x is a half or 3. So those are the two positive roots. And that's question 12 complete. Question 13. Right, I need to show that x plus 4 is a factor of this function of x. So I'm going to substitute in x is minus 4 and see if the function gives me a value of 0. So that's going to be minus 4 cubed minus 2 times 16 minus 19 times minus 4 plus 20. And a bit of calculator action finds that that does indeed equal 0. So that would imply that x plus 4 is a factor. Good. Okay, part B. Hence or otherwise find solutions to that equation. Right, well, let's write down the equation. X cubed minus 2x squared minus 19x plus 20 equals 0. And I'm going to obviously factorise that. So I'm going to have x plus 4 Now I'm going to factorise the rest by inspection. It's going to be x squared there, gives me 4 of them, and I want to therefore have minus 6 of them, gives me plus 20, gives me minus 24, so I want to add on 5, and 4 times 5 is indeed 20. Good. And so now I'm going to see if I can't factorise any further. I'm going to need both of these brackets to be x minuses. It's going to be 5 and 1. So the solutions to the equation are x equals minus 4, 5, or 1. And that is question 13 complete. Question 14. I've got to show that f of x, which is this expression, 6x cubed plus 17x squared minus 5x minus 6, can be written as 3x minus 2 lots of something. So I could do a long division. I'm going to divide this by inspection here. So I'm going to have 2x squared here, which is going to give me minus 4x squared. So I'm going to want to add on another 21 because I've already got 3x there. I'm going to need a 7x there. That gives me minus 14. And I want to have minus 5, so I'm going to need to add 9, so I'm going to need a plus 3 here. And minus 2 times plus 3 is indeed minus 6, so that's looking good. Okay, so now I have found A, B, and C. A is 2, B is 7, and C is 3. Part B, factorise f of x completely, so I'm guessing that I can factorise it further. So I've got 3x minus 2. Now I'm going to try and split this second bracket into 2. Clearly 2x and x, clearly plus and plus, and clearly 3 and 1. Good. Write down all the roots of the equation f of x equals 0. Well, their roots are going to be 2/3, minus 3 over 2, and minus a half. Question 14 done. Question 15. Right, I've got to prove the expression on the left is equal to the expression on the right. So I'm going to start with the expression on the left, and I'm going to try to simplify that. What I'm going to do is I'm going to multiply top and bottom by root x plus root y. Okay, so on the top, I'm going to have x times root x. Actually, I'm not going to multiply out the top. I'm just going to keep the top as it is. X minus y, lots of root x plus root y. And I'm going to multiply out the bottom here. So I'm going to have root x times root x, so that's x. The middle terms are going to disappear. Then I'm going to have minus root y times root y, which is y. And look at that. Now I can divide top and bottom by x minus y, which leaves me simply with root x plus root y, which is what I was asked to prove. So that is question 15 done. Question 16. Use completing the square to prove that this expression is always positive. Okay, well, let's see what happens, shall we? So I'm going to complete the square. So that's going to be n minus 4 squared minus 16 plus 20. So that expression is equal to n minus 4 squared plus 4. So how does that prove that it's positive for all values of x? Well, for all values of x, n minus 4 squared is always greater than or equal to 0. Therefore, n minus 4 squared plus 4 is always greater than or equal to 4, i.e. positive. That is question 16 done. Question 17. I've got 4 points here, which are the vertices of a quadrilateral, and I need to prove that the quadrilateral is a square. So one of the sides is obviously going to be AB. One of the sides is BC. One of the sides is CD, and one of the sides is DA. What I'm going to do is I'm going to find the length of all four sides, and if all four sides have an equal length, then it's either a square or a rhombus, and then I'm going to confirm that the gradients mean that these sides are perpendicular to each other. Okay, so let's have a look first of all at the length of AB. So AB here will be the square root of 2 squared plus 1 squared, which is the square root of 5. BC is the square root of 1 squared plus 2 squared. There we go. Good. CD is the square root of 2 squared plus 1 squared. Good. And DA is the square root of, and again, 1 squared plus 2 squared. Good. So they all have the same length. Right, let's look at their gradients, shall we? So I'm going to call it m each time. So the difference in the y, so I'm going to do 2 minus 1 over 3 minus 1 gives me a gradient there of a half. Right, what about the gradient in this case? Let's do the bottom minus the top. So I'm going to have 0 minus 2 and 4 minus 3 gives me a gradient of minus 2 over 1 minus 2, which incidentally is the negative reciprocal there. So that's looking good. Let's check the gradient here. Let's do the top minus the bottom. 0 minus minus 1 over 4 minus 2 is a half. Okay, and let's do the gradient here. Let's do the bottom minus the top. 1 minus minus 1 and 1 minus 2, which gives me 2 over minus 1, gives me minus 2. Look at that. So I have shown that AB equals BC equals CD equals DA, and I have shown that AB is parallel to CD, and I've shown that BC is parallel to DA, and I've shown that AB is perpendicular to BC. So I think I have proved now that that is a quadrilateral, that quadrilateral is a square. Question 18. Prove the sum of 2 consecutive positive odd numbers less than 10 gives an even number. Well, there can't be too many combinations for me to try here, so I'll do this by exhaustion. 2 consecutive positive odd numbers less than 10. So I'm either dealing with 1 and 3, or I'm dealing with 3 and 5, or I'm dealing with 5 and 7, or I'm dealing with 7 and 9. Those are the only possibilities, aren't they? And let me just show that all of those sums are indeed even numbers. I believe I've done it. That's question 18 done. Prove that the statement n squared minus n plus 3 is a prime number for all values of n is untrue. Well, I'm going to try and prove that by contradiction. I'm going to find an n which gives me an answer which is not prime. Let's try n is 1. Then it's going to be 1 minus 1 plus 3. It's prime. Let's try n is 2. Then it's 4 minus 2 plus 3 is 5 is prime. Let's try n is 3. Then it's 9 minus 3 plus 3, which is 9, not prime. There we go. Job done. Question 20. I've got to prove the left-hand side is equal to the right-hand side. Now, sometimes one takes the left-hand side and manipulates it, and you end up with something which is the same as the expression on the right. Sometimes you take the right-hand side and manipulate it, and end up with something which is the same as the expression on the left. Or sometimes you manipulate the expression on the left a little, get an expression, manipulate the expression on the right a little, and get that same expression. It's best just to play it by ear really and see what turns out to be easiest. So I'm going to manipulate the expression on the left here. Before I start, I'm going to write everything as fractional, or as in terms of indices in powers. So I'm going to write that first bracket as that, and the second bracket is already written using index notation. Right, so I'm going to multiply out these brackets now. So am I going to add the powers, of course? So x times x to the power of 4 over 3 is x to the power of 7 over 3. X times plus x to the power of minus 2 over 3 is x to the power of a third. Right, minus x to the power of minus 1 multiplied by x to the power of 4 thirds. It's going to be minus x, add the indices, to the power of a third. And then minus x to the power of minus 1 multiplied by x to the power of minus 2 thirds is minus x, add the indices, minus 5 thirds. Now those two middle terms are going to cancel each other out, of course. So I'm left with that. Now, I'm going to take the expression on the right now, see what happens when I simplify that. Again, I'll start by making sure that everything's written in an easy fashion. So I'm simply going to change that 1 over x squared to x to the power of minus 2. Right, let's multiply out that bracket, shall we? So I add the indices, so x to the power of 2 and a third, that's x to the power of 7 over 3, minus x to the power of, I've got a third, add minus 2, which is going to be minus 5 over 3. And look at that, that is the same as that. So I have proved that those two expressions are indeed equal, and that's number 20 finished. Question 21. Right, well what I'm going to do here is I'm simply going to take my brackets on the right hand side, multiply them out, and hope that I get what is written on the left hand side. So let's have a look. It's x plus 4 multiplied by x minus 5, 2x plus 3. So that's going to be x plus 4. Now I'm going to multiply out these second brackets here. So it's 2x squared minus 10x plus 3x is minus 7x minus 15. So that's going to equal x lots of the first bracket, x lots of the second bracket. So I'm looking at the second bracket, and I'm simply multiplying everything by x, and then plus 4 lots of the second bracket. So I'm looking at the second bracket, and I'm simply multiplying everything by 4. And now I'm going to collect like terms. 2x cubed minus 7x squared plus 8x squared is plus an x squared. Minus 15x minus 28x is minus 43x minus 60 at the end. Look at that. That's question 21 done. Question 22. I have an equation, and the equation is x squared minus kx plus k equals 0, where k is positive. Now, where this equation has two equal roots, then it says prove that k must be 4. Well, if this equation is going to have two equal roots, then it needs to only have one solution, which means the discriminant must equal 0. So what this is asking me to do is to show that if the discriminant equals 0, then k must be 4. So let's say that the discriminant must be 0. So that means that b squared minus 4ac must be 0. Why is that? Because there is only one solution. Okay, b squared is going to be minus k squared minus 4 times 1 times k, and that apparently must be 0, as there's only one solution. K squared minus 4k must equal 0. So k squared must equal 4k, so k must be 4. Look at that. The discriminant equaling one solution means the discriminant 0. The discriminant 0 means that k is 4. Job done. Question 23. Prove that the distance between the opposite edges of a regular hexagon of side length root 3 is a rational value. Well, let's explore this by drawing a regular hexagon, or roughly a regular hexagon. Here we go. and that has side lengths of root 3. And I'm asked to show that the distance between opposite edges, so that distance, is rational. Well, I wonder if I can find that distance anyway, because a hexagon is made up of equilateral triangles, like that. So if I take one of those equilateral triangles, here it is, that's root 3 there. I need to find this height, which I'll call h. That's root 3 over 2, isn't it? So h is going to be the square root of root 3 squared minus root 3 over 2 squared. So that's going to be the square root of 3 minus 3 over 4, which is the square root of 2 1/4, which is the square root of 9 over 4, which is 3 over 2. So this length here is 3 over 2. Which length? That length is 3 over 2. So the whole distance is going to be twice that, isn't it? So the distance is going to be 3 over 2 times 2, which equals 3, which is rational. So I have proved that the distance between the opposite edges of a regular hexagon is a rational value. In fact, I've shown it's 3, but I proved it's rational. End of question 23. Question 24. Prove that the difference of the squares of two consecutive even numbers is always divisible by 4. So two consecutive even numbers, well, 2n is an even number, and the next even number is 2n plus 2. Let's look at the squares of those. That's 4n squared, and this is 2n plus 2 multiplied by 2n plus 2, which is 4n squared plus 8n plus 4. So the difference is 8n plus 4. And can I show that that's always divisible by 4? Yes, because I can write it as a multiple of 4. So there we go, that's that done. Part B, is this statement true for odd numbers? Well, let's have a look. So two consecutive odd numbers. So an odd number could be 2n minus 1, and the next odd number would be 2n plus 1. Let's square both of those, shall we? 2n minus 1 squared would be 4n squared minus 4n plus 1, and 2n plus 1 squared is 2n plus 1 multiplied by 2n plus 1, which is 4n squared plus 4n plus 1. Let's look at the difference of those, shall we? We'll take the larger and we'll subtract the smaller. Okay, we'll be careful of our signs. Plus 4n minus 1 gives me 8n, which of course is a multiple of 4. It's because it can be written as 4 multiplied by something. So yes, it is. Okay, that is question 24. Question 25. A student is trying to prove that 1 plus x squared is always less than 1 plus x squared. The student writes that 1 plus x all squared equals, okay, that does equal, yes it does, 1 plus 2x plus x squared. And he then states that 1 plus x squared is less than that. So he thinks he's proved it. Identify the error made in the proof. Well, I'm afraid to say that this is only less than that if 2x is positive, isn't it? Because just to illustrate that, you could subtract 1 plus x squared from both sides, and you'd be left with the condition that 2x is greater than 0. So you're assuming that x is greater than 0. But if x is negative, then his proof is flawed, isn't it? So identify the error made in the proof. X could be negative. Good. Provide a counterexample to show that the statement is not true. Well, I suppose if I just take a counterexample of x being negative, that'll do it, won't it? So let's take x equals minus 1 and see what happens. So 1 plus minus 1 squared. And is that going to be less than 1 plus minus 1 all squared? Let's have a look. Well, that's 1 plus 1. Is that less than 0 squared? No. Okay, I think we provided a counterexample. And that's the end of question 25.